Today's tech talk will be given by Moritz of DKRZ and René Redler of the Max Planck Institute. And those two guys have asked me not to praise them for the work they've done, but to focus on YAC and YAC2 instead. So as far as I get it, in 2011, they were faced with the need for improvement in the existing coupler. And looking at that code, they decided to write a new coupler from scratch and use C as a programming language and modern software development methods like unit tests, but are still pretty rarely used in climate science. And as far as I understand, Moritz at some point decided to repeat the whole exercise and develop YAC2. I guess he's going to improve my description a bit in his talk. And until last week, I figured that the coupler was the last piece of model that I would ever touch voluntarily. But did a little bit of debugging on Icon, and I figured that YAC is very useful and a great animal. So I'm looking forward to learning more about how to use YAC and what it actually does. And I think this is gonna really help us a lot in our life with a model. So Moritz, the floor is yours for the first part, and then René will talk about this use of YAC in the second part.
Thank you very much for the introduction and for organizing this. YAC stands for yet another coupler, because there were quite a lot of couplers on, or there were some couplers on the market, and we wrote another one. So that's where the name comes from. Oops. Now I need to get to the next slide. Yeah, that works. René and myself didn't do it on our own. We had the help of some students and contributions from other people from DKRZ and the Max Planck Institute. So not a two-man team, but we had some help. YAC is a library very similar to Oasis. You link it to a component where the component is, for example, the ocean or the atmosphere model. You configure it via an XML file. It supports all common grid types currently available. It contains various 2D interpolation methods, and all these methods support the computation of the weights online and in parallel. That means for your run, you don't need to provide any weight files or anything, because the computation of the weights is so performant that it doesn't have any significant impact on the overall runtime. The current version is 1.5.5, but as Florian mentioned, I did a major rewrite for the last couple of months, and the version 2 should be released this or next week, I think, depending on when we have time to test. So how do you use it? So in your model run, you start by initializing YAC on all processes. For the initialization, YAC requires the configuration XML file, which needs to be the same on all processes. Then each process provides information about its part of the grid and what fields it locally has and where the field is located, whether on the cell or a corner of a cell, and if it is on a cell, if it is at the middle point of the cell or at some edge or something. And once all required information is provided, you tell YAC to complete the initialization. It will then start computing the weights and setting up some communication patterns, and will do some organization work. It might require some external weight files if you configure it to do so. And you can also configure it to write out weight files for the ones being computed online. Afterwards, you start your standard time loop, and you can exchange data between components using the put and get operations commonly used in other couplers as well. Once you're finished, you finalize YAC, and it will free all the memory that was consumed by it. Here's some examples of grids that are being supported by YAC. On the top left, you have a standard Gaussian grid. Below that, a Gaussian reduced grid. In the middle, you have some somewhat regular grids with local refinements in missing cells. And on the right-hand side, you have your typical unstructured grids. We have a number of different interpolations, simplest one being a simple average method, where you, when you have a target point, you search for the source cells matching that point and do an average of the values associated to the corners of that source cell and interpolate it based on that. Then we have a first and second order conservative interpolation, an n-nearest neighbor interpolation, and for the n-nearest neighbor and the average, we have various weighting options. That means an arithmetic mean, distance weighted, Gauss weighted, and yeah. In addition, we have a method we call source point mapping, which is used within Icon to do the river runoff. And then, which is quite unique to YAC, is a higher order method for point-based data called hybrid cubic spherical Bernstein-Bezier patch interpolation, called Bernstein-Bezier. Its resulting field has contiguous first derivatives, and it is a replacement for the patch recovery available in ESMF. And the result is similar to that of the bicubic interpolation that you might know from the script library. We can also read in weights from files, but we only support our own weight file format because, to my knowledge, the other formats are too limited. We have also introduced a new concept for interpolation called Interpolation Stack. We have here a small example where we started by interpolating a field using a conservative first order interpolation. But in this configuration, it failed for all target cells that were covered completely or partially by land cells. That means, so all the land cells didn't get any value, and some of the coast cells also didn't get values. The cells that failed for the first order conservative were then passed to a patch recovery method, which was available in YAC 1, or is still available, but will not be available probably in YAC 2. And that method could much better handle the cells along the coast, but still the land cells didn't get any value. And these cells are then passed to a fixed interpolation where the user can select a fixed value, which you can see at the bottom with all the gray cells, or now land cells that get somewhat any fixed value that you want. Any interpolation in YAC consists of such a stack with at least one method. The user can select the number of interpolations within the stack, and he can freely select any of the available methods for each stage of the stack. Currently, the Surfax Institute in France is doing a comparison of the quality of interpolations by different libraries providing interpolation capabilities. This comparison includes the script library, ESMF library, XRS, and YAC. The results should be released soon within the ISENIS project. They compared different methods listed here. So they compared the bilinear interpolation from script and ESMF with our average combined with a 2 nearest neighbor with distance weighting. Then they compared first and second order conservative interpolation, a 1 nearest neighbor interpolation, and the higher order methods from each of the libraries. And for all tests, YAC performed quite well. There were a couple of minor problems which were fixed quite easily, and now it's comparable to the other libraries in all aspects. Basically, yeah. Regarding performance, because if you want to do it online, you expect it to be quite quick. For that, I did some measurements with 2 toy models, where one model used a cubed sphere with around 4 million cells, and the other one used a Icon grid, specifically an Icon R2B11 with over 300 million cells. As you can see, this is a quite high resolution setup. So this is a really extreme case. I did a 2-way coupling, so both fields could send data to the respective other model. I measured the time that YAC took to compute the weights and to set up the communication patterns. And I measured the time an exchange took, where an exchange is a where both models send data at the same time and receive at the same time, and then I measure the time it takes to do the whole operation. And I used a first-order conservative in this test case. On the horizontal axis, you have number of nodes per component, where one node had 24 processes, and I did all the tests on Mistral. And for both diagrams, you see a good scaling behavior. And even for this very high resolution test case, the initialization time is, from my perspective, way within reasonable bounds. So way below 100 seconds for even, that is, I think, 8 nodes per component, and scales then quite well. As you can imagine, if you have a more typical setup with less cells, timings are much better. Just to give a quick overview of what you can expect from the configuration file. On the right-hand side, you have an example XML file. You're not supposed to actually read this. This is just an overview. The XML file starts with a list of components that will take part in the coupling. In this case, we have 3 components, 1, 2, and 3. And then you list the fields that will be available in the overall setup, and assign the fields to the respective component. Afterwards, you specify each coupling individually, where you there you set which component is the source, which is the target. You set a coupling frequency, and then you define the interpolation stack for each coupling individually. And that's it for my quick introduction. And René should continue with a more in-depth look at how YAC is used within Icon. Thanks for listening.
So coming now to the integration or interplay between YAC and Icon. So what I'm describing here is not mainly my work, but based on work from Marco Giorgetta, Stefan Lorenz, Rainer Schnoll, Helmut Haag, Irene Stemmler, who mainly worked on the physical interface. And then Sergei Kazurin, we gave him some headaches of integrating YAC into the current Icon building system. Maybe there were others, so apologies for those I do not mention here. So as a default, YAC will be compiled together with Icon. So when you check out Icon and you configure it, YAC is built aside with it. If you don't want to do that, you have to disable the coupling at the configure step. And recently I noticed that the people from the DWD disabled the coupling, the building of YAC by default. Martin Köhler, can you tell more about that? But if in order to build YAC at DWD, you have then explicitly to enable coupling with YAC. So as Moritz mentioned, so it's not YAC itself, and the whole philosophy is not as different as we had it in our previous MPI-M. So it's a library that handles the interpolation and redistribution amongst the physical fields and between the atmosphere and the ocean. So it's basically the same schematic view in Icon ESM, where you have the atmosphere component, the ocean, and the land scheme. What Moritz mentioned here is he already mentioned that we have several phases to consider: the initialization phase, then the definition phase, which is completed by the call to the search, which does the major part of the work in this part, and then the data exchange inside the time loop and the finalization. In the following, I will only concentrate then on 2 of those calls, the grid definition and getting the data. We provide a tutorial where you can find more details and in-depth information for how to use the different calls and other information which we will show at the end. So how the interface to YAC is implemented in Icon, that is currently done in the current releases. It's basically located in 3 files. So there is one module file for the atmosphere, and here only for the ICOM physics. I will come to NWP later. Then there is a small part in JS-Bach, which handles the runoff, and then another module file for the ocean. And for the atmosphere and the ocean, so there are, each contains 3 subroutines, one for the initialization and phase terminated by the search, then another subroutine for the data exchange, and then the destruction to terminate YAC. So coupling to the NWP physics is appearing at the horizon, and there we propose a slightly new structure and rearrangement of routines that is not yet settled, so still under investigation and has to be confirmed, but be aware that things might change a little bit. So as the grid definition is the same for the ICOM physics and the NWP physics in the atmosphere, proposal is to have the definition phase separated out into one file and one routine, which is then called, while the data exchange itself is different for the ICOM physics and the NWP physics, simply because the arrays live at different places. For the ocean, there's no change, hopefully. So the data exchange, whether the ocean exchanges data with the NWP or the ICOM physics, that should hopefully make no difference from the ocean side. JS-Bach is still unchanged, and maybe we will decide to handle the coupling interface of the runoff a little bit different than it is done now. Having a look into the Fortran code itself, so the interface to YAC is pretty neat. You load the module file. So first for the initialization with a construction and destruction routine and another logical variable. Yes, so if it's a coupled run, you call the construction, which does all the grid field and component definition. And at the end of the time loop, if it's a coupled run, you destruct YAC. And likewise for the data exchange itself. So you load the module, which has the put and FGET calls implemented. You just call it. And that's it from Icon, and all the, say, everything else is handled then behind this in the subroutine. Moritz already mentioned the XML file that for the coupled configurations that we support so far, that is included in the run script templates. And in red, you see the shell command, which parses then this XML section and writes it into a coupling XML file. And at the same time, replaces some shell variables with some reasonable input that is also coming from the run script. So here it's an abstract model name, but it's also then done for different time steps and other variables in the XML file. We provide a graphical user interface so that you can also generate your own coupling XML file and yes, do whatever you want with that. And also for further details, we would like to refer to our tutorial. Of course, there's a connection between the XML file and the Fortran interface. Here you see this grid definition. That is just the first abstract call to define a grid, which provides a grid name. And this same name has to appear in the XML file. Otherwise, you will get an error. And then the whole part of defining center points, edges, and connectivity in YAC 1. And that is not what we describe here. but that is also then part of our tutorial. Would like then to briefly touch upon the exchange phase of data, how it is implemented in Icon currently. But I mean, you could follow the same logical pattern for the coupling of any other component. So there's nothing particular to Icon in how this the sequence of calls is set up. So you start from a restart file where the initial data are read from, or it could be also initial conditions. But let's assume here for simplicity that everything is contained in a restart to continue an integration. Then each side, atmosphere and ocean, calls then inside this module subroutine, which I briefly mentioned. There is an fput called, which stores the data into the library, and then at a coupling time step, then the data is actually interpolated and redistributed and sent to the remote site where it can be get at the matching FGET call at the same coupling time step. Time steps can be different, and likewise the calls to the fput, but one only has to guarantee that there are matching times for the put and get call so that the data can be exchanged. And these are the synchronization points between the two components, and I will come to that at the end again. So, and of course, all event handling is done by MTime, so we use the MTime library to do the event handling inside YAC. Let's focus a little bit on the FGET call here as an example. So you call it the YAC FGET with a field ID, which you got from the initialization phase, and then the collection size, then a receive buffer, an info argument, also the receive buffer on which you receive the data, if it's a coupling time step and it's actually filled by YAC, and then an info argument is also returned, which tells you whether something has been filled in or not. So this YAC FGET can be called at every time step. And then accumulation averaging is done inside YAC, or on the other side at the put. And then the FGET would then receive the accumulated or averaged fields, or there's also a possibility to exchange instantaneous fields. So a deeper look into the code, you call the YAC FGET. You have again this field ID, the receive buffer, and then the info argument tells you whether you have to do some action. And in this case, so if info tells you, yes, I've received data, then the input of the buffer has to be copied back to the icon fields. And here you can see that we only provide, the data structure provides only one-dimensional arrays for the horizontal. So we do not support this nblock and proma structure in icon, or for block structured irregular grids, this idim, jdim dimensions. So that all has to be stored in a one-dimensional array, and of course the grid is then be set accordingly. And also to be noted that YAC doesn't work on the halo region, so it only works on the active part. And so after filling the data again, in icon, you have to call this in patch array to fill the halo cells. Yes, brief look in this info argument. So these are the numbers that can be returned, and something between 1 and 6 tells you that you have to do something after the FGET or fput call. And none would mean there no coupling has happened. That can either be that there was no coupling time step. So, and then accumulation can happen in between, or yes, if instantaneous coupling has been chosen, then the in-between calls wouldn't do anything, but only at the coupling time steps data would be exchanged. So brief look into the graphical user interface that was how to set up the XML file. So each component comes with a list of physical fields that's just names, and then you can load them into the graphical user interface. You can give it a direction. So heat flux goes from atmosphere to ocean, and seawater velocity goes from ocean to atmosphere. Green indicates that for this transfer, an interpolation stack has already been defined. Red means there's no interpolation stack available yet. And then if you click on this, you enter the next step where you can define the interpolation stack that Moritz already mentioned. So it's 3, but you can even add more interpolations to the stack if it makes sense. And you can also provide then source and target time step coupling period. This is handled separately for each field, so you can couple different fields at different coupling periods, with different operations, accumulation, and of course with different interpolation stacks. Yes, and then a short remark on the timing. So Moritz already mentioned some timings from his toy model at 1 kilometer resolution. This is another example from our 5 kilometer coupled run. Here, a total time of the job was 1600 seconds. And then you can see the initialization phase took here in this real example 5 seconds for the ocean in this case. No, it was, well, for one component, can't remember whether it was atmosphere ocean. And you see the other component took almost a minute, but that was mainly due to waiting time. So this 5 seconds is really the work that has to be done for the search, while the other part was still waiting, to wait for the other component to reach its initialization phase, because of the reading in input data takes a different amount of time on each side. So, but here we can't do anything about it. That is the way, this imbalance we have to live with during the initialization phase. And then you have this data exchange. You start with a collection of put calls. So first, each side puts the data to the library to make it available, and then it goes into the MPI layer. And then it's followed by a stack of FGET calls to receive data. And once the first GET is served, then MPI guarantees that all the other GETs can be served as well. So it's really the first GET call that counts. And we also do not measure in Icon the very first GET call, because that is still polluted by load rebalancing due to the initialization phase and reading in of all sorts of input data. But then what we measure then, the second and subsequent first GET calls tells you something about load balancing. And what you can see here, that the ocean is waiting almost 10,000 seconds for the data to be received, while the atmosphere almost always gets the data already because the ocean has delivered it and it's ready to send. And to get an ideal load balancing, you would like to get these numbers onto equal levels. So in our case, that would mean that we would have to either decrease the number of ocean nodes to make it slower, or increase the number of atmosphere nodes, or play around with the time steps. So whatever is possible there. Yes, and then I'm already at the end for presentation. So YAC is documented on the Doxygen page. We provide the link. There you can see configuration examples for different systems if you want to compile YAC as a standalone library for your own purposes. And you find then also a detailed description of the Fortran and C interface and some other more or less useful information. And yeah, again, you see the link to our Doxygen page. You can get released versions of YAC from our Git repository, and all documentation is also available with further links at the DKRZ site, Dienst Softwareentwicklung. Yeah, thanks a lot.
Thanks a lot, René.